Okay, good evening, everyone.
Good evening, ma'am.
Good
Good
evening.
evening, ma'am.
Good evening. Welcome to today's class. Uh, so I am now starting my presentation and sharing my slides. So, so today we will be discussing our block 2, that is stereochemistry 2, which consists of your configuration and its correlation. About the configuration, yesterday also we discussed something. Then, oh sorry, this is topicity, not toxicity. By mistake it is written toxicity. Okay, topicity and prostereoisomerism, asymmetric induction, molecular disymmetry, and chirooptical properties. These are the 4 units we will be discussing today. So, first is our configuration and correlation. Yesterday we have discussed about what are your conformations and conformers. Conformational isomers, those are your conformers. So conformers are the same compound which are interchangeable through a rotation about a sigma bond. But when we have a double bond or we have a restricted rotation, you cannot rotate through this carbon carbon double bond. So in that case there is no conformers, but these two are also stereoisomers. These are also your configurational isomers. This is also known as your geometrical isomers. So stereoisomers have different compounds and they are not interchangeable. Okay, so which we have already discussed, stereoisomers can be enantiomers or diastereomers. Enantiomers are mirror images of each other, and diastereomers are not mirror images. And also, this type of carbon carbon double bond where we have, these are also stereoisomers and they are not mirror images. So these are also known as your diastereomers. Not only in case of your single bonded compounds we have diastereomers, but in case of your carbon carbon double bond where we have sufficient substituents, then we can have also diastereomers. So in case of this we have the nomenclature as your cis and trans. So when these groups, you see the carbon carbon double bond, when these like groups are on opposite sides, then that is named as trans, and when they are on the same side, they are named as cis. Or you can just say it from hydrogen. If hydrogen is on the same side of the bond, that is your cis, and when it is on the opposite side of the double bond, then that is named as your trans. Even this is also, but where your cis and trans alkene fails. So in case of a terminal alkene, you do not have stereoisomers because both the substituents are similar. Here also you have both the substituents or the identical groups are similar. You have two identical groups, so this is also not cis and trans. So when we cannot say cis and trans always. Just see this example. In this case, we do not have hydrogens or similar kind of groups. So here it is difficult to name them as cis or trans. So there are other kind of nomenclature that is known as your EZ nomenclature. So in E and Z nomenclature, so Z in Z configuration, your lower, we just give the substituent some priorities. If the lower priority are on the same side and higher priorities are on same side, that is named as Z. And when the low priorities are on opposite side or your higher priorities are on opposite sides, that is known as your E configuration. So suppose you just see this one. In this case, you have to apply the CIP rule here as we have applied in case of our RS configuration nomenclature. So here iodine is having higher atomic number and bromine has been lower atomic number. So this is our first priority, this is our second priority. And in this carbon atom, we have chlorine is our first priority and fluorine is your second priority. So high priority group are on the same sides and low priority group are on your same side. So in this case, this is your Z, but when they are of opposite, here this is priority 1, this is priority 1, this is priority 2, and this is priority 2. So they are on opposite side, we tell it at E configuration. So this CIP rule can engulf Rilla growths. So each carbon in the pi bond is attached to two substituents. For each carbon, these two substituents are ranked according to the atomic numbers. Such as chlorine will be ranked first as compared to fluorine. If the ranked one are on the same side, we say it as Z, which is the short form of Juzamine, that is together. And if ranked one are on opposite side of the pi bond, then we describe it as E. E is antigen, that is, which means your opposite. So, and when the priority is to be decided between the atoms which are isotopes of the same element, suppose we have hydrogen and deuterium, then deuterium will get higher priority as compared to hydrogen. And when the two groups are attached to the carbon atom involved in the formation of double bond have the same atoms as points of attachment, then the priorities are assigned according to the first point of difference. Suppose it's not working. Oh, my computer got hanged, I think. Okay, sorry, I will be back in a minute. I'm just checking what happened to this one. Okay, sorry for the interruption. Actually, I got some problem in my computer. So now I am sharing my screen. The screen is being visible.
Yes, ma'am.
Yes, ma'am.
Okay, where were we? I think we were here. Okay, so this rule suggests that when ranked ones are on the same side, we have to give the designation as G, and when it is on the opposite side, we have to give the designation as E. This protocol, which we have already seen, that when bromine is your higher priority on this carbon and chlorine is of higher priority on this carbon and they are on the same side, so this would be of your Z. And in this case, your higher priority bromine is on this side and higher priority chlorine of this carbon is on the opposite side. Then that has to be E. But in this question, in this one, you see on this carbon, we have two different groups, bromine and one ethyl. So it is easy for this one is 1 and this one is 2. But what about this? Here you have a carbon and on this side also you have a carbon. In this case, you have to see the next point of attachment. In the next point of attachment, if you just see here, your next point of attachment in the on this side is again carbon, then hydrogen. But here the next type of attachment is oxygen and hydrogen. So this one would be this this side would be given higher priority as compared to this one. So in this case, your high rank 1 or higher priority groups are on the same side, so this is going to be Z. So you can just assign EZ notations to any of any molecules. Suppose I will just, these are the actually ranking who is going to be in the higher priority. So this is the order. Okay, suppose we go for this molecule. I am not doing the all. So in this case, this carbon, this is the carbon carbon double bond pi bond here. So this is going to be priority 1 and this is going to be priority number 2, because the next point of attachment here is carbon and here it is chlorine. Okay, bromine is there in far uh, per distance, so we have to give this one first priority, this is one priority number 2. And in this carbon, here you have a first point of attachment is carbon and here your first point of attachment is also carbon. So in this case, you have a carbon next to it and then another carbon next to it, but in this case you have two carbons next to it, so this is going to be in the first priority and this is going to be second priority, so this would be assigned as Z. And in this case, here you have, this is the carbon carbon double bond, so this one is first priority and this one is going to be second priority because nitrogen will come before your carbon. And in this case, if you just see, these two are same, these two are same, so this is not, you do not have a stereoisomer here. If on one side you have both the substituents are same, then that is not a stereoisomer. Okay. Next is configurational notations for our optical isomers, like yesterday for enantiomers or diastereomers. And that is, we have discussed about it yesterday already. That is your DL system nomenclature, where we are assigning the chiral carbon DRL according to L-glyceraldehyde and D-glyceraldehyde. So whichever chiral group has OH group or any that kind of group on the right, as in your D-glyceraldehyde, that will be assigned as D. And when your OH or NH2, that kind of groups is on left, as in your L-glyceraldehyde, that will be assigned L. And array system, that is again we have discussed yesterday. So on a chiral center, you have to follow your this CIP rules to determine R and S on a chiral center. First, you give the priority, then you view along your lowest priority group. If from going 1 to 2 to 3, if it traces the path in a clockwise direction, then you assign R. When it is in a counterclockwise or anti-clockwise direction while tracing the path from 1 to 2 to 3, then it would be assigned as S. And remember, the hydrogen, that is the lowest priority in this case, or any other group who is the lowest priority, that should be actually placed away from the viewer, or that fourth rank should be in a dashed wedge, or in our Fisher. Okay, I have not given the Fisher projection formula here, but in our Fisher projection, this fourth priority group should not be placed in a horizontal position. It should be placed in a vertical position. If it is present in your horizontal position, then also if your assign while tracing the path from 1 to 2 to 3, if it goes clockwise, then assign it S, just opposite, reverse the order, which we have already discussed in yesterday's class. So next one is how we determine the configurations of your any chiral center. So you can do in different methods. Actually, two methods are given here. First one is by chemical correlation. So in this method, suppose you have to just start with suppose we have to determine, like, this is your glyceraldehyde with the carbon number 2 is your stereogenic center. Okay, we do not know what is the actually the configuration of this carbon number 2. So when it is converted to tartaric acid, it can be converted to tartaric acid. If you just see, the carbon number 2 remains the same, just we have incorporated another carbon. Oh, sorry, the carbon number 3 remains the same. We have just incorporated one, this 1 and 2. These are being incorporated in your tartaric acid. So the center 2, carbon 2, is now here 3, that is in your tartaric acid, that has the same, it has not been changed, only the reaction has been taken place in carbon number 1. So how, if you just do the reaction, you see when this aldehyde group is treated with hydrogen cyanide, so it first gives you a cyanohydrin, which upon hydrolysis gives you the acid. So in this transformation, your carbon number 2, the stereo center or the configuration of carbon number 2 when it is converted to tartaric acid, that is your carbon number 3, but it is remaining the same because it is untouched in this transformation. So it was just seen that when this tartaric acid, and this one is your optically active, so this can have three tartaric acids. Okay, we have in all, we have three tartaric acids. Okay, glyceraldehyde gives you tartaric acid, so we have three tartaric acid, which we have yesterday discussed. So that is your three stereoisomers. Okay, and so these two are your mirror images, and you have a mesotartaric acid. So if you just see, okay, the carbon number 2, okay, in case of this structure 2, in this case the stereo center at this one has different geometry. Okay, this center is different, but in this case the other two tartaric acid has the same your stereo configuration. So from this you can just consider that, okay, this has to be your diglyceraldehyde. So similarly, you can just say that your D-serine, okay, which can be converted to compound A, okay, where you can just see that your carbon center 2 is not changed, only only the carbon number 3 is affected. So its its configuration is remain unchanged. So this A can be also uh, we get from one amide by Hofmann degradation, and this amide again can be converted to your aspartic acid. So from this, actually we know the configuration of D-serine, where NH2 group is on the right side and it is giving the same compound A, which can give, which can be got from your amide by Hofmann degradation, which can again be converted to your aspartic acid. So by this correlation, you can just say that this aspartic acid has the same configuration at this carbon number 2 as in D-serine. So this is your configuration by chemical correlation. Okay. Next is the method of quasi-racemates. So what is quasi-racemate? Quasi-racemate is a co-crystal of two similar but distinct compounds, one of which is left-handed and the other one is right-handed. Okay, they are similar compounds. They are not the same compounds enantiomer. They are similar compounds, but they are similar but distinct. Suppose I just take the case of your chlorosuccinic acid. This one is your chlorosuccinic acid, and this one is your bromosuccinic acid. They are just almost mirror image relationship. Okay, such compounds, so they are sterically similar and are still able to form a racemic crystalline phase. So when we just mix these two, they form a compound. Actually, they form a solution. So such compounds are known as your quasi-racemates. Okay, so these quasi-racemates, actually, if this one is plus, then means if this one is dextrorotatory in this direction, this one is your levorotatory. These are similar but not the same compound. So if these two are form a solution, okay, they form a solution or they form a compound, actually they form a compound, then that gives a phase diagram like this. And if the plus isomer of chlorosuccinic acid and your plus isomer of bromosuccinic acid is mixed, that just gives you a mixture, and its phase diagram looks like this. So this is for the compound which forms a compound for your plus chlorosuccinic acid and your minus bromosuccinic acid, so which forms a your racemate. But in this case, that is quasi-racemate. We know racemate is the mixture of two enantiomer of the same compound, but in this case we are using the term quasi-racemate to just quasi-racemate means here both the enantiomers are not from the same compound, but they are of the similar compound. So if one is dextrorotatory, the other one is your levorotatory. So when we just mix those, that form a quasi-racemate, and that gives you a phase diagram like this. But when they both are of the same configuration, then that gives you a mixture, and that gives you a phase diagram like this. Suppose you do not know the configuration of any configuration of any compound. Okay, so what you do, you just mix it with a known configuration of something, okay, which is similar to its structure and compound. So if it is of opposite configuration, that would give you a phase diagram like this. So from that you can just know that if this one is dextrorotatory, the other one would be your levorotatory. If it does not give, if the other one is of the same dextrorotatory, then that is going to give you a mixture. So in that case you would get a phase diagram like this. So this is the in this way you can know the configuration of your supplied compound or whatever you are having with you. Next is comes your topicity and pro-stereoisomerism. We have stereoisomerism. So what is your pro-stereoisomerism and topicity? So you just see this molecule here. Here we have two hydrogens on this carbon. So in this case, these two hydrogens are apparently identical. So these are known as your homomorphic. So or we can just tell them as ligands also. Sometimes they are used as ligands because if carbon is your central atom, then these are attached to this carbon. So these are named as ligands also. So these ligands or these atoms are in isolation, have the same form and indistinguishable, but such ligands are distinguishable when present as a part of a molecule. So here you will see that okay, they are the same. How they can be distinguishable when it is part of a molecule? So suppose we just you just see the same molecule. I have just named H1 and H2 here. So if I replace this H1 by F, I will get this compound, and if I replace this H2 by F, I would get this compound. So now if you just see, now this carbon contains 4 different ligands. So now this is a chiral carbon. And if you see, these two are enantiomers. They are no longer same. So that means this hydrogen's position, the position of this hydrogen, where this hydrogen is present, that is although homomorphic, but that is not a same position. So this special relationship between these two hydrogens is known as your topicity. So if you just see, it is our first priority, second, third, fourth. So while going from 1 to 2 to 3, that goes anti-clockwise, but hydrogen is on the horizontal position, so it has to be R, and then it is S. So these two replacement of hydrogens, this hydrogen gives R enantiomer and this hydrogen gives your S enantiomer. So these two hydrogens are known as your enantiotopic or heterotopic. They are giving you different enantiomers. So they are no longer same. So homomorphic ligands can be now classified into homotopic or heterotopic, such as in this case, whether you just replace this hydrogen uh, with any atom, fluorine, so that is going to give CH3, C, CH3, F, H, or whether this side also it is going to give you the same compound, because that is no longer, that is not a chiral compound. So these two hydrogens are giving you same compound, so these are homotopic. So when these two hydrogens are replaced by any other groups that is giving you different stereoisomers, then those are known as your heterotopic. And in this case, these stereoisomers are enantiomers, so those are known as your enantiotopic. Suppose we have already have a chiral center here, and just consider the hydrogens here at carbon number 3. Suppose I replace this hydrogens by chlorine. Let us see, if we replace this hydrogen by chlorine, hydrogen 1 by chlorine, that we are going to get this compound, and this upper part is remaining the same, but when we are replacing this hydrogen number 2 by chlorine, we are getting this compound. So now these two are not enantiomers, because we already have a stereocenter here and we are generating another stereocenter here. So in this case, these two are not mirror images, but they are diastereomers. Okay, we have more than one stereocenter, so we remember that from yesterday's class, when we already have a stereocenter, when we are inducing chirality there, then there is chances of getting your diastereomers. So here there are diastereomers. So these two hydrogens are again heterotopic, but in this case we will say this as diastereotopic. So our homomorphic hydrogens can be of two types: homomeric and heteromeric. Homotopic and heterotopic. Again, heterotopic can be your enantiotopic or diastereotopic. Uh, Similarly, this hydrogen 1 and 2, uh, if you just replace this, so they are going to give you diastereomers. So these are known as your diastereotopic. These hydrogens are diastereotopic. Even this hydrogen number, your 1 and 2, those, when they are replaced, those are also going to give you diastereoisomers, so they are also diastereotopic. So from this, we just get to know that our homomorphic ligands can be divided into homotopic and heterotopic. And this heterotopic are also, we can just say this as stereoheterotopic, which can be enantiotopic and diastereotopic. So there is ligands are now homotopic, heterotopic, enantiotopic, and diastereotopic. But sometimes we have a homotopic phases or heterotopic or enantiotopic phases. Suppose take the example of this carbonyl carbon. Okay, when we have both of the groups are same. So if our MGX, your Grignard reagent, is going to attack from this side, or it is going to attack from this side. So if it is going to attack from top, then OH is coming here. If it is going to attack from, but in this case, this is not a chiral atom, so these are the homotopic phases. So this is the site of attack, so that is known as your phase. Okay, but when we have a aldehyde, other aldehyde rather than your formaldehyde, so in that case, your similarly the R can attack from top phase or it can attack from the bottom phase. But in this case, it is going to give you two enantiomers. Although it is going to give you equal ratio of enantiomer that results in your racemic mixture, but we can say that these phases are your enantiotopic phases, as it is giving you enantiomers. So uh, enantiotopic or diastereotopic ligands, and these are your phases. Phase means that is the site of your reaction, whether top phase it is attacking from the top phase or it is attacking from the bottom phase. So how we will name the stereo heterotopic ligands actually. So in this case, as we have already considered, in this case when we are replacing hydrogen by, suppose here I have just replaced it by deuterium, so it is giving you uh, R configuration, and when this hydrogen is replaced, that is giving you S configuration. So this hydrogen is known as, named as pro R, and this hydrogen is known as your pro S, which we the actually the uh, name is your pro stereo isomerism. Okay, so pro means it is after one reaction, or it is one reaction or one step away from your chiral center. So that's why this is known as your pro R, and as this one is going to give you a S enantiomer by the replacement of this hydrogen that gives you a S enantiomer. This hydrogen is named as pro S, and this hydrogen after replacement gives you a R enantiomer, so that is given as pro R. So similarly, the stereoheterotopic phases can also be named or can also be given the actually assign the configurations can be assigned to your stereoheterotopic phases. So suppose consider this ethanol, which we have done the Grignard reagent. So you can just if the attack is from the top side, then you just view it from the top side. When you are viewing it from the top side, the while tracing the path from 1 to 2 to 3, that goes in a clockwise direction, so that is known as your re phase. And when you view it from the downside, actually this one is the arrow is pointing wrong actually. First, when you view it from this side, you have to have an imagination that when you are viewing from the below the surface, below this one, then you have to move your eyes from first priority, then second priority, then third priority in an anti-clockwise manner. So this one is your C phase. Re is from rectus and SI is from your sinister. So this is the nomenclature of stereoheterotopic, your ligands as well as phases. Next comes your stereogenicity, or what is your, which remains stereogenic center, or the study of your stereogenic compounds, that would be your stereogenicity. So what is a stereocenter? A stereocenter is an atom or a group of atoms if the interchange of two ligands attached to it results in a new stereoisomer. As the stereoisomerism is generated by such a center, it is called a stereogenic center. Suppose consider this carbon. Okay, we have 4 different groups. If you just interchange two ligands, just their position is being interchanged, and you are getting a different new stereoisomer, then this carbon is known as your stereogenic center. Okay, so if we just check this one, in this case, this is your mesotartaric acid. So you interchange your ligands at C3. 1, 2, 3. This is your 4. So here OH is on the left side. Just you interchange the ligands at your position number 3. So in this case, if you are interchanging your ligands at C3, these are not giving you your enantiomer. That is not going to give you a same that is not going to give you a different isomer. The reason is, if you just they are not you see they are not enantiomers because they are diastereomers, but still but they are not enantiomers, but they are diastereomers. Still it is giving you a stereoisomer. So this center 3 is a stereogenic center. Even center 2 also is a stereogenic center. Although you are not getting enantiomers, but still you are getting diastereomers, and that is also a stereoisomer. And even when you do not have a chiral center, although you are having a chiral axis also, there you have a stereogenic centers or stereoisomers are present here, which we have already discussed in the last class, like your in case of your allenes. So what is chirotopicity? Chirotopicity is the phenomenon related to the presence of a chirotopic atom. What is a chirotopic atom? A chirotopic atom is an atom which resides in a chiral environment. If that atom is residing in a chiral environment, then that is known as your chirotopic. Suppose you consider this molecule. So in this case, this is a chiral carbon. So all these points, they are all chiral points. So these are chirotopic. All these points or all these atoms are your chirotopic, or this carbon is your chirotopic. But however, achiral molecules may also have many chirotopic atoms or point. Just illustrate in the case of your mesotartaric acid. So we know that this mesotartaric acid, we have a plane of symmetry. That's why those are known as, that is known as your mesotartaric acid. The upper half is just exactly the mirror image of your lower half. So that this compound is not chiral, although you have stereogenic centers, which we already actually checked now. These have stereogenic centers, but that is not a chiral molecule. So in this case, you have a plane of symmetry. So this one here, you do not have any chiral environment. But if we just say this one and this one, you have chirotopic atoms are there, because there you have those are your chiral environment is there. Okay, just see the molecule here. This
ଏଇଟା
molecule is
କାଇରାଲ କାହିଁକି ହେଲାନି
କୋଉଟା?
ଏଇଟା
এই
ଯୋଉଟା
এই total molecule ଟା କାଲି କହିଥିଲି, this whole molecule actually ତାର chirotopic ଅଛି କୋଉଠି? এই center ଗୁଡାକ chirotopic ଅଛି, because that those are in your chiral environment. Okay, this molecule is not chiral because you have a plane of symmetry. The upper half is exactly the mirror image of your lower half. ହେଲା, ତେଣୁ upper half ଯଦି plus r direction ରେ ଯାଉଛି, ଏଟା ମାନେ plus clockwise ଯିବ, ଏଟା anti clockwise ଯାଏ। ତେଣୁ ଏଟା mutual compensation or internal compensation ହବା ଦ୍ୱାରା ସେ orbital actually ସେ optical rotation ଦବ ନାହିଁ। So this molecule as such is not chiral. But ଏଠି କହୁଛି କି achiral molecules may also have many chirotopic atoms or points. So here the plane of symmetry, এই জায়গাটা তোমার achiral, but this as a molecule whole, this is not a chiral molecule. But these points, okay, these points are chirotopic, because chirotopicity ର ଅର୍ଥ ହେଲା is an atom which resides in a chiral environment. Okay, this one is chiral environment, this one is your chiral environment. As such, this molecule is not chiral. ବୁଝିପାରିଲ?
ଆଜ୍ଞା ଆଜ୍ଞା ସେଣ୍ଟର ଗୁରା କାଇରୋଟୋପିକ କିନ୍ତୁ ମଲିକ୍ୟୁଲ ଟା କାଇରୋଟୋପିକ ନୁହଁ
molecule ଟା chiral ନୁହଁ, ହେଲା?
କାଇରାଲ ନୁହଁ ସରି ସରି
ହଁ
ସରି
ହଁ, chiral ନୁହଁ। chiral ଆମର
କାରଣ
କେତେବେଳେ
ମିରର
ବୁଝିଲେ
ଇମେଜ ଅଫ
ଯେତେବେଳେ
ଇଚ ଅଦର
ହଁ, mirror image ଟା mirror image ଖାଲି ହବନି, mirror images are not superimposable or they rotate the plane polarized light. Okay,
ଆଜ୍ଞା
here this cannot rotate the plane polarized light. Okay,
ଆଜ୍ଞା
this molecule, here you see this molecule is chiral. So all the points in it should be chirotopic. So just check the this actually stereogenicity at C3. So if you just see the stereogenicity at C3, you just exchange, ଆମେ ଜାଣିତେ stereogenic center କେତେବେଳେ ହବ? When we exchange the ligands attached to this stereogenic center. So just at C3, we have now put the, here OH was in the left side, we have given it on the right hand side. You just okay, from this carbon you have done this one. Then again, when you just rotate it, when you rotate it at 180 degree, you will see that these two are same. You are getting the same structure. So that means your carbon number 3 is not a stereogenic center. Okay, carbon number 3 is not a stereogenic center, but it is chirotopic. Okay, because it is in a chiral environment. There is no mirror plane of symmetry or nothing, but still it is not a stereogenic center because its interchange is giving you the same structure, not a stereoisomer, but it is in a chiral environment. So carbon number 3 is a actually chirotopic but not stereogenic. Okay, what is pseudo asymmetry? Well, in the last class, I just escaped it because it was again in this unit, and so we can just discuss it here. Again, you just take the example of ribaric acid. Okay, you just see this is not your tartaric acid. Here another carbon is increased. So here the plane of symmetry is along your carbon number 3. So in ribaric acid, you have a plane of symmetry. So as this molecule is your uh, this molecule is not chiral. Okay, because this is also a meso compound. You have plane of symmetry. So C3, as it is not in a chiral environment, that would be achirotopic. So now just consider, now let us see whether this C3 carbon, okay, is stereogenic or not. What we will do, we will just exchange the position or interchange the ligands. Okay, interchange the ligands. It here your ligand is on hydrogen is on the left and here OH is on the right. When you are interchanging OH on your left and hydrogen on your right, so when that is also giving you a another mesoisomer. Okay, so these two XX and XXI, they are your not mirror image, so they are diastereomers, and we have to now check whether that is giving us the same compound, same uh, center or same structure. If you just now rotate it, so now this comes 1 2 3 4 5, and you see these two are not same. These two are not same, means this one is not has the same structure as this one, that is would be different. So this has a, this carbon number 3 is a stereogenic center, although it is achirotopic, but this is a stereogenic center. Carbon number 3 has a stereogenic center. So now this one is achirotopic and it has 4 different ligands. Suppose we just consider this carbon number 3. Now you check, this has 4 different ligands. How you will know? You can just say this one is same, the blue one and this pink one are same. It will be looking same to you, although they are structurally same and their joint is also same. If you just consider their configuration, you will see that they too have different configuration. If you just check this carbon number 2, okay, in carbon number 2 your oxygen is of higher priority, this one is of second, and the substituent here, okay, I am just for carbon number 2 I am doing here. So your COH group is here and your OH is here, your hydrogen is here, and here this group. So this is your first priority, second, and this one is third. And by doing so, it is going from 1 to 2 to 3 in anticlockwise, but hydrogen is on your horizontal one. So this has to be R. S, as it is going anticlockwise, it will be S, but we have to reverse it, so it is going to give you R configuration. Similarly, you can just see that the lower half would have a S configuration. So now, although you can just say that you are having same type of groups, but no, they are configurationally different. So this center, this carbon number 3 center, that is a stereogenic center, and now you have different configuration on both the side of it, that is known as your pseudo asymmetric center. So when a tetrahedral carbon is attached to 4 different groups, where 2 of them are configurationally different, although they are same groups, but they are configurationally different. That is, one is R and another is S. Such a center is called pseudo asymmetric center, and this phenomenon is called your pseudo asymmetry. Okay, so if you have to give the configuration to this carbon, this compound, what configuration you would give? So first, this one will be of higher priority, and from CIP rule, always R will give higher priority as compared to S. So 1 2 3, and this is 4. So as it is going in anticlockwise and hydrogen is on the horizontal side, So this one has to be R. So in this case, as it is a meso compound, you have to give the small r, okay, not capital R. And in this case, the other enantiomer, suppose the starting material. So in this case, your this one is R, this one is S, but OH is on this side, 1, 2, 3. So it was going clockwise, but hydrogen is in the horizontal bond. So it has to be your S and small s. Okay, they are named like this because not to get confused with R and S, capital R and capital S, they are given name small r and small s. Here always capital R gets more priority as compared to S. Like R configuration always gets more priority as compared to S. So that is known as your pseudo asymmetry. When you have a chiral center which is attached to 4 different groups, and among these 4 different groups, 2 groups are configurationally different. That is, one is R and one is S. That center is called your pseudo asymmetric center. Next comes your stereogenic and prochiral centers. Okay, so you see, when we have this kind of keto group, when we are adding anything, we are generating a chiral compound. So this center, we are generating a stereogenic center. So from which compound? The previous compound is having a center here where you are attacking it, and from there you are getting a stereogenic center. So this one is known as your prochiral center. As we get prochiral ligand, so this one is your prochiral centers. So that is going to give you 2 enantiomers. So that's why this is known as your stereogenic center. Don't get confused with chirotopic phases, enantiotopic phase, enantiotopic phases, and these are your center. This is the center, that one is your phase. Okay, so when we have both the substituents on this ketone are same, then you are not getting any okay, this one is being merged actually. So here you are not getting a chiral center, although we have written it like this. The OH is means the cyanide is attacking from this, so their relativity is opposite to each other, but still they are not chiral. So this is not a prochiral center. So this is not a prochiral center. Even when we exchange these hydrogens with deuterium, that gives us enantiomers. So this carbon is a prochiral center, and it is giving you stereogenic centers. So prochiral center, when we replace it with another group, we get a new stereogenic center. So prochiral centers are those centers which can be converted to chiral center by one single transformation. If 2 such or chemical transformations are required, then such a center is called prochiral. If we need 2 steps, then that would be your prochiral center. Any doubt till now? Any doubt? Anyone is listening or not?
Hello.
Hello?
Hello. Yes, ma'am.
Am I audible or not?
Yes, ma'am. Yeah.
Okay. Is there any doubt?
No, ma'am. Ma'am, no, ma'am. It's clear.
Madam, quasi-decimate. Madam,
Quasi-decimate. Okay, quasi-decimate. Yeah, that is a that is a method to know the configuration, or to just give the configuration of a compound. Suppose you have a chiral compound. Okay, you do not know what is its configuration. Okay, you just know that this is my compound, but you do not know what is its configuration, whether it is R or it is S. Depending on R or S, you can just say it is having this configuration, or this group is on top or this group is on down. So what you do is like you form a quasi-racement. So you have to take another compound whose configuration you know. Okay, you know its configuration. So suppose you know which one you are taking. You know that it is dextro-rotatory. Okay, I will go to the second one. Okay, yeah, if you whatever you are taking, that is the known configuration, it is your plus enantiomer, and you do not know what kind of enantiomer or what kind of configuration you are having. You know the compound what it is. Okay, you know whether it is means which kind of product. Suppose you are having an alcohol. Okay, you are having an alcohol where you are having uh, okay, butanol. So you do not know whether it is this butanol or this butanol. Okay, but you are taking another compound whose configuration you know exactly. So whether suppose it is your dextrorotatory, so you do not know what is the configuration of this one. So if you mix these two, and this forms a solution or a compound, okay, its phase diagram will look like this. Okay, this would be the phase diagram when it forms with a another one, which gives you a phase diagram of like this. So when this type of phase diagram is known, so it has to be mixed with a minus or levorotatory, then only it will give you a this type of phase diagram. ओके माने तमे कौन करथिबो गोटाकर कॉन्फ़िगरेशन तमे ऑलरेडी जानिछ किंतु यार कॉन्फ़िगरेशन तमे जानि ना. ओके सो ये ता सहित जेतबेले मिसेइबो जदि सी तुमको ए टाइप रो फेज डायग्राम दउची, दैट मीन्स दिस इज द फेज डायग्राम ऑफ ए क्वाजी रेसिमेट. ओके सो इन दैट केस तमे श्योर हे जिवो कि निश्चित भाबरे सेटा माइनस हेथिबो बोली. जदि से ता सहित मिसिले फेज डायग्राम क्वाजी रेसिमेट नबनी कि गोटे conglomerate banuchi, then in that case that will give a phase diagram of like that. Then you know that okay, this is not levorotatory, that one is your dextrorotatory. बुझी पारलो तो जेमिति कि एठी क्लोरोसक्सिनिक एसिड आउ ब्रोमोसक्सिनिक एसिड. Okay, chlorosuccinic acid is your plus, but bromosuccinic acid is levo, but they form a quasi racemate. जेमती racemic mixture amar hotla plus or minus मिसी गले racemic mixture, but that is of the same compound. So in case of quasi racemate you have to take different compound that they have to be similar, and one, if one is right handed, the other one has to be left handed, then only that will form a quasi racemate. And हे गले तो बुझिला.
हाँ मैडम.
Okay. Okay, next comes your asymmetric induction. Okay, asymmetric induction means up to now we know that okay, what are enantiomers, what are diastereomers, how you can deduce the configuration by this, but also we have also studied like how you get your enantiomer by resolution of your racemic mixtures. Yesterday we have done like chromatographic separation and some chemical methods. We have discussed all those. So there is another thing that is known as your asymmetric synthesis. So in asymmetric synthesis, from an achiral compound, you can just get your enantiomers or asymmetric compounds. So that is known as your asymmetric synthesis. You can either get enantiomer or diastereomers in preference to one another. Suppose there is the possibility of two enantiomers, you are getting one enantiomer in excess, which we have discussed what is optical purity or enantiomeric excess. So this kind of synthesis is known as your asymmetric synthesis. So there are some rules like we have now studied what is your phases, prochiral phases. So from which side your group has to attack to give. If from this side the group is attacking, you are getting one enantiomer, and if it is attacking from the bottom side, you are getting other enantiomer. So there are some rules which depicts that which side will be attacked. So first rule is known as your Cramp's rule. So according to this rule, so he has done this rule mostly for your ketones, nucleophilic addition reactions to your ketones. which like mostly your Grignard reagent, nucleophilic addition, or lithium aluminum hydride attack. So those are actually studied for nucleophilic addition reactions of ketones. So which already have a chiral carbon attached at alpha position. Actually, this is your alpha position, and three groups are attached to the chiral center. Suppose this one, you just take this one. Now these three groups can be actually labeled as small, medium, and large. So this one is your large, this one is your medium group, and this one is your small group. So the preferred conformation for the attack by nucleophile, so it will always prefer to attack from the small site. Wherever you have the a smaller group or smaller, you see you have a at the alpha position you have three groups. The nucleophile will attack from your less hindered site, otherwise it would face some steric interaction. So according to this would approach from this carbonyl carbon from your uh, smaller group, so which gives rise to your major product. That way you just see here you are attacking C6H5 minus, that is your nucleophile, that is attacking from the side where your hydrogen is already there. So you just see hydrogen was dashed line, so C6H5 is now your dashed line, and OH will go top. So that gives you your major product of this one, where C6H5 is attacking from your smaller size group, and the other you are getting as a minor product. Or he has given some model, so he has placed the carbonyl means the molecule in such a way that actually Newman's projection in such a way that the large group is present opposite to the carbonyl carbon. Okay, the large group is present opposite to your carbonyl carbon, and R group is there. Or here we have H, so you can just put it H, and the large group is present just opposite to this one, and then these are H and CH3. So now the nucleophile can attack from this side or from this side, so it will prefer to attack near your hydrogen, the smaller side where you have your smaller groups. So suppose we have lithium aluminum hydride. Here the nucleophile is H minus. So now it will attack from this side again. From this side, so resulting in, as it is dash from, this is your smaller group, so again your H is also dash. So this is going to give you the major product, this is your minor product. So you can just see how it is doing. Actually this oxygen is coordinating with magnesium, and again C6H5 is attacking from this side. It cannot attack from this side because it will face steric hindrance from this side. So according to Cramp's rule, whenever your nucleophile is attacking your carbonyl carbon, it will attack from the smaller side. So he proposed a model in which in the Newman projection, the carbonyl carbon and the large group are on opposite side. Then you can just put your smaller groups and it will attack from the smaller side where you have your smaller. So another dipolar model was suggested where you have a strongly electronegative group such as halogen group is present at the carbon alpha to the carbonyl carbon. So instead, in that case, your large group will not remain here. Rather, your electronegative group will be present opposite to the carbonyl group. So now again the preferred attack of your nucleophile will be from that side where you have smaller groups. So this was Cramp's rule, but Cramp's rule could not explain the reduction of cyclohexanones when we have you see we have a large group, and when we have a very large group, when you have a very large group, here the medium size interaction there will be have more actually steric hindrance. In this case you will have more steric hindrance. So Felkin, what he did, he proposed another actually rule or another model. Actually these are all models. So where what he did, that the larger group and your carbonyl carbon are not present now antiperiplanar or in opposite direction, but rather they are present in perpendicular way. And here also the point of or the site of attack would be from your smaller from that side where you have your smaller groups. So you just see in this case, your nucleophile will it can have these two different type of conformations. Okay, so in this case, the medium conformation, medium ring is just nearer to your larger group, and in this conformation, uh, you have this, and in this way here S is nearer to your R. So there would be less steric hindrance in this conformation as compared to this conformation. So the major product will be by the attack of nucleophile from this side to give you the major product. So next comes your Frelux rule. So Frelux rule just extended your Cramps rule, in which the chiral alcohols and your alpha hydroxy acids, alpha hydroxy, yes, alpha hydroxy acid, and this one is your alpha keto, alpha keto ester. Okay, so it correlates the configuration of chiral alcohols and alpha hydroxy acids. So suppose you just take this alpha keto ester, it has a alcohol part where that is your chiral alcohol. Okay, so this chiral alcohol has a smaller group, medium size group, and large size group. So in this case, when your it is treated with Grignard reagent, so it will attack from the side of your smaller group. So it will attack from the side of the smaller group, and you see your smaller group is in a actually solid wedge. So R dash would be your solid wedge of the plane, because that is approaching from that side only. So wedge has no where to go, so it would be your backward, or R dash would be front, and this one OH would be back. So now when you hydrolyze it, it is going to give you alpha hydroxy acid. So next is your what are the type of selectivity in organic reactions. Like we are saying that one is your major product, one is your minor product. So these are selective reactions, we can say. So there are different type of selectivity. One is chemoselectivity, like which chemical group or which functional group is going to attack. So you have a carbon-carbon triple bond here, and you have a carbon-carbon double bond here. So when you are using Lindlar's catalyst, it selectively adds to hydrogen in presence of alkenes. Actually, this alkene is not being shown here. So it would just that uh, okay. So that would be your chemoselectively, means one functional group will be reacted, other functional group will not be reacted. So that would be your chemoselectivity. Regioselectivity. So when we have the addition of HBr, you know the Markovnikov's rule. So here we have a major regioisomer. The hydrogen can attack this position or that position depending on your Markovnikov's rule. Okay, so that is your regioselectivity, which position it is attacking. Next comes your stereoselectivity. So in case of stereoselectivity, so you have selectivity for formation of one stereoisomer over another. As we know, our SN2 reaction always gives your inversion in configuration. That means if we start with S enantiomer, we always get a R enantiomer. So this is a kind of your nucleophilic substitution reaction in your SN2 mechanism that always gives you R enantiomer. So that is your stereoselective. Another one is your enantioselectivity. Suppose this reaction, when we are doing epoxidation, we can get two enantiomers. So one enantiomer we are getting in excess as compared to the other enantiomer. So this is known as your enantioselectivity. So again, the stereoselective reactions, one can be stereospecific, another is stereoselective. So stereoselective comes when you have, like you are taking any kind of reactant, and you are preferably getting one major, another one your minor one. But stereospecific means when you are taking a specific compound and it is going to give you a specific product, and that is your stereospecific. Suppose one enantiomer or one stereoisomer is giving this product only, and its other diastereomer is giving you different product, and that is known as your stereospecific. So your stereospecific and stereoselective, I have written here or not? Okay. Okay, I just forgot to write what is stereoselective or stereospecific. Okay, one enantiomer stereoselective reactions are called stereospecific when the stereochemistry of the static material completely determines the stereochemistry of the product. Suppose we are taking cis alkene, then it will give this specific product, and when we are taking trans alkene, that is going to give you specific product. So we will do the actually examples here. So just see this reaction. This is an elimination reaction. Here you get a E alkene as the major enantiomer, but also you get some Z alkene. So here this is a stereoselective reaction, not a stereospecific reaction. But in some cases you would get stereospecific reactions also. Suppose we take the SN2 nucleophilic substitution in your SN2 mechanism. So in that case, when you are taking this reactant or substrate, so you are going to get only the inversion in country. Suppose you start with R, you will always get S, or if you start with S, you would always get R. So the stereochemistry of the starting material determines the stereochemistry of your product. So that reaction is known as your stereospecificity. But in case of your SN1 reaction, substitution nucleophilic unimolecular reaction, in that case, you get different, you start with whatever starting material you take R or S, whatever you are taking, you are always getting some racemic product. So this SN1 reaction does not have your stereochemical preference, whereas SN2 reaction are stereospecific in nature. Suppose in this case, you just see, in case of cis butene, when we do the bromination, okay, that gives cis bromine give you enantiomers. But in case of transbutene, that gives you a single compound. So product C and D are not too different, they are the same compounds, but still we know that cis-butene give you enantiomers, and in case of transbutene, that gives you your meso 2,3-dibromobutane, which is the diastereomer of this compound. These two, this C and B, or they are diastereomers. So these reactions are also stereospecific because cis-butene gives you enantiomers and transbutene gives you some diastereomers. So these are stereospecific reactions. But when comes your stereoselective, any compound you are taking, suppose we are just taking CH3, COCH3, C2H5. When we are just doing hydrogenation, we are getting one preferably over another. So this one is your stereoselective reaction. Okay. Or many stereoselective reactions are there. Next comes your diastereoselectivity. So here we are getting enantioselectivity. Next is your diastereoselectivity. So diastereoselectivity means you are already having your some centers, but when you are doing epoxidation, you are getting two different diastereomers. Okay, one would be your major product, the other one would be your minor product. So here in diastereoselective reactions, one diastereomer would be formed preferentially. So this is your diastereoselective reactions. Okay, just a minute, I will just take. So in this epoxidation reaction, we can have a major product and a minor product, and the relation between these two are diastereomers. Actually, as these CH3 groups are on top, the major product is coming when your oxygen from your metachloroforbandic acid is actually attacking from downside. So that's why you are getting your major product. But you can also get your minor product when this one will actually flip, and that would give you a minor product. But this reaction is your diastereoselective. So qualitative correlation between conformation and reactivity. What would be the reactions and what would be the reaction outcomes, means on which factor this depends. We can just summarize in like our substrates or reactants can be conformationally rigid diastereomers or conformationally mobile diastereomers, or substrates with two or more conformers. Okay, so what is conformationally rigid diastereomers? So in case of conformationally rigid diastereomers, just you see this trans 2 alpha decalol and trans 2 beta decalol. These are conformationally rigid. You cannot interconvert this to this. This cannot be interconverted. And these are also the trans isomer and the cis isomers. They cannot be interconverted. So whenever you have these two rigid diastereomers, you have a mixture of these two diastereomers, then one is going to react faster, one is going to react slower. As it was seen that this is going to react faster and this one is going to react actually slower. The axial enantiomer, axial diastereomer reacts slower. So next is conformationally mobile diastereomers. And these uh, two diastereomers of 2,3,4 triphenyl butyric acid. One is your threophone, one is in your erythrophone. So in this case, these two diastereomers on cyclization with HF yield two different products. Okay, it gives two different products. One gives a 5-membered ring and one a 6-membered ring. The other one gives your indanone. Actually, these diastereomers, they are actually, that depends mostly on their conformation. So here if you see this, in case of trio, this CH2 group is most closer to your COH group. So you are getting a actually this C6H5, its ortho position here, the CH2. Okay, that is forming a bond with this COH group. But in case of your erythro, now this CH2 C6H5 is exactly opposite of this one, whereas this C6H5 is present nearer to this COH group. So now cyclization occurs in between these two, so resulting in a formation of a 5-membered ring, and this one gives you a 6-membered ring. So these two diastereomers are giving two different products. So again, when we have substrates with two or more conformation, these conformers or these diastereomers are not interchangeable. But when you have some conformers which are interchangeable, or they actually get converted to one another. So for such substrate, the overall specific reaction rate depends on the specific reaction rates of the conformers and the ground state population of the conformers. So, K is equal to summation over Ni Ki. So Ki is the specific reaction of conformer and mole fraction of the ith conformer. So that depends like how many conformers we are having, means we can have a different type of conformers. So which conformer and how much population is there, so the rate of overall reaction rate will depend on that. So again, these conformers could be homomeric, like they behave identically with respect to the rate of the reaction and product forms. They can be enantiomeric, behave identically under achiral conditions but differently under chiral conditions. They can be diastereomeric, behave differently always. So these conformers can be homomeric, enantiomeric, or diastereomeric. Such as when you have this cyclohexanone, 4-methyl cyclohexanone. So in this case, when you treat it with one chiral compound, so it gives one enantiomer that was present in your larger amount. The other one we could have got if our we get on this position. Okay, so this one is not being formed this carbon number 2 and carbon number 6, they are enantiotopic. When we are reacting with your optically active isooctyl nitrite, that gives you 2 oxy immunoderivative, which are actually we can get it at carbon number 2 or carbon number 6, but this gives only at carbon number 2. So only it give you one enantiomer in larger amount than the other. But in case of your malic acid, you just see these two hydrogens. These two hydrogens are actually your, we will see whether they are diastereotopic or enantiotopic. Okay, these two hydrogens, actually, if you just see, they are in equilibrium with each other. Like sometimes it can go on this side, H2, H1. So they are actually, if this H1 is removed, you are getting malic acid, and if this H2 is removed, you are getting fumaric acid. So you are getting two different diastereomers. So but they are in a equilibrating mixture. Actually, they are present in equal amounts. So depending on the reaction rate, you may get fumaric acid or you may get malic acid. So these two hydrogens are your diastereotopic, because you are getting diastereoisomers, diastereotopic, you are getting two different diastereomers. But again, depending on the reaction rate and depending on their because these two are of equal energy, we will come next in your Cotton-Hammett principle, which one will get means which one we will get and which one actually would be the major product. So you can have different type of conformations or conformers in your reaction mixture, and you can get different type of your products depending on your conformers. So the product formation depends on what? Okay, which product will be formed? So that mostly depends on your reaction rate. So that is actually, that belongs to your Cotton-Hammett principle. So in Cotton-Hammett principle, it correlates the product distribution with the transition state energies formed by the two conformers. Okay, suppose we have this substrate. Okay, it has two conformers, A and B, and they are interchangeable. Okay, so they are interchangeable or conversions. This A can be converted to B or B can be converted to A, but A is going to give rise to a different product and B is going to give rise to a different product. Suppose their rate constant for this is Kc, this one is Kd, this one are K1 and K2. So we know that the rate of a reaction depends on the energy of activation. Energy of activation. This is the minimum amount of energy required for a reaction. So this is the energy of activation. If this is the energy of reactant, this is the energy of product. So this is the energy of activation, and this one is actually your transition state. So in transition, what is transition state? That is the actually your maximum energy state. Okay, it has to pass through that transition state barrier for doing your reaction. So the less this activation energy, the reaction rate would be faster. So in this case, actually we can have different type of situations. The in the both the conformers can be of same energy or different energy, or their reaction rate can be different. So there are, we have four different possible ways. First one is, you have the more stable conformer giving the major product, provided the rate of reaction of more stable conformation is higher. So you just see here we have two conformers, A and this one is B. So A is at lower energy as compared to B. So A is the more stable conformer. So in this case, more stable conformer. And again, from A to C, the energy of activation is less as compared to when transferring from B to D. That energy of activation is higher. So in that case, this one would give you the more, this stable conformer would give you the major product. Suppose you just check with your cis-butene and trans-butene. Okay, in case of cis-butene and trans-butene is more stable. And again, from trans-butene, okay, this From trans-butene, when you do the addition of HBr, this would be in this direction. Okay, addition of HBr, it would be easier for trans-butene. So this goes through a lower transition state because there would be less interaction in case of your, this is the, there would be actually less interaction in your transition state, so that would be more stable, so less energy. But in this case, you just see here you have two gauge interaction, CH3 groups are closer to each other. So in this case, the transition state would be higher in energy. So it would be its production, like from bromination, your cis butene. So the product actually in this case, we would have bromine here and hydrogen. Okay, another hydrogen. But so here the transition state would be higher, so the product actually would be from the your more stable conformer, because that is passing through a lower energy transition state. Next one is when you have a less stable conformer giving the major product, provided the rate of reaction of less stable conformation is higher. Rate of reaction rate is higher means in that case it passes through a lower energy transition state. Just check here, you have in this two, you have this one is your more stable transformer, a more stable conformer, and this one is your less stable conformer. But this less stable conformer goes through a pathway which is of less energy as compared to the more stable conformer, which goes through a higher energy. So this one, this rate of reaction would be faster, this one would be slower. So you would get this one as major product and this one would be your minor product. And when you have the conformer in equal, both the conformers are of same energy, in that case, what would be your driving force? Which one reacts faster? Which one will react faster? Who passes through a lower energy transition state. So here B will give you the major product and A will give you your minor product. So in this transform, you just see it can be either di-equatorial or it can be diaxial. You can just flip it, but diaxial only gives you the product because it goes through a lower energy transition state. Next is when both the conformers, another one, when both the conformers are of equal energy. You can just interconvert it. This is their interconversion diagram. But one goes through a low energy pathway and another goes through a high energy pathway. So this is the case of your asymmetric catalysis, where your beta keto esters are giving your actually stereoselective products. So in this case, you get here it goes through a low energy pathway, so that reacts faster, and this one will react slower. I just put it again or what? Okay. Okay, which we have already told that these two carbons can react with this chiral compound to give you only one enantiomer is getting, the other enantiomer we are not getting. Although they both are the you have both probability, but one is going through forming this enantiomer that is going through a less energy pathway as compared to the other one. And this malic acid, fumaric acid, actually you are going to get this trans isomer faster as compared to malic acid. This one is your cis, because that goes through a lower energy reaction state, transition state. Your last unit of today's class, molecular dissymmetry and chirooptical properties. How this dissymmetry in molecules are behaving in presence of our optical, like in presence of your light plane polarized light or circularly polarized light. So these are your plane polarized light. You have a electric vector as well as your magnetic component. So that is oscillating in one plane. So suppose when these two waves are exactly at the same place at the same time, then the magnitudes of their respective electric and magnetic vectors will simply add to each other to give the resultant wave of double magnitude of electric field vector as well as your magnetic field vector. So when two waves are exactly at the same place at the same time, the magnitude will act. But when the two waves exist in the same region of space but have different direction, okay, uh, so their addition will yield the resultant vectors in different orientation. So suppose again, but one of them, you have two waves but one of them is moving ahead of the other, they are not moving in the same time. So in that case we were going to get a like this helix or circular uh, type of light. So such a light in which the electromagnetic wave continuously rotate in the same direction is called your circularly polarized light. One of them is called your left hand circular polarized light, another one is your right hand circular polarized light. If you just mix these two, that would give you linearly polarized light. So what is circular birefringence and optical rotation? So when linearly polarized light is passes through the disymmetric medium such as calcite or any your disymmetric medium, so in that case it has two components. It's two components, that is your left circularly polarized light and the right circularly polarized light exhibit two different refractive indices. That means your left component will travel right circularly polarized light make travel faster, or the light your left circularly polarized light travel faster. If nr is less than nl, so in that case your right circularly polarized light will travel faster. So in that case the material is called to be dextrorotatory because this one is traveling faster and has positive specific rotation. The situation is other way around for your laboratory materials. Okay, on traversing the circularly birefringent medium, the phase relationship between the circularly polarized waves changes and the resultant linearly polarized wave actually rotates. So when this is your optical rotation. Using a polarimeter, you can find out the optical rotation of a compound. So when you are measuring your optical rotation, actually we just previously said that our your chiral compounds rotate the plane polarized light, but in that case we are taking the plane polarized light of a specific wavelength. When we are measuring the optical rotation as a function of wavelength, that is termed as optical rotatory dispersion. Means we will measure the optical rotation at a different wavelength of your light, but when we are just taking the specific rotation, we are taking it at a particular wavelength. And in case of circular dichroism, what we do, our left circularly polarized light and right circularly polarized light will be observed at different extents. So for instance, suppose our chiral, it is previously like this is your right circularly polarized light, this one is your left circularly polarized light. When you pass through a chiral medium or any disymmetrical molecule, suppose your means that is your right circularly polarized light is absorbed more. In that case it would have a uh, in that case it that vector will be less. The right circularly polarized light vector will be less as compared to your left circularly polarized light. So in that case, that is not a now circularly polarized light, that would behave as a elliptically polarized light. So in this case, actually in circular dichroism, it is measured as a function of wavelength. Okay, so function of wavelength in terms of your absorbance, like the difference in observance, difference in your observance of right circularly polarized light and left circularly polarized light versus your wavelength, and that is known as your circular dichroism spectroscopy. Okay, we do not have to go very detailed into your this spectroscopic techniques because we just need the application part. So in case of optical rotatory dispersion and your CD curves, we can have. Okay, so in case of optically rotatory dispersion, I think I have already shown you how we do this instruments. We have a polarizer monochromator, then a polarizer. Monochromator means it will just pass a single a light of a particular wavelength, then that would polarize to give you a linearly polarized light. Then we have a sample and we can just analyze here. So this plain ORD curves, we can, when we actually plot a graph between your wavelength and optical rotation, that is calculating the optical rotation at different lengths, we can get a positive curve or a negative curve. In a positive curve, as you see, with increase in with decrease in wavelength, your optical rotation increases, and in a negative curve, with decrease in wavelength, your optical rotation decreases. So if on approaching the region of cotton effect, then comes your cotton effect. What is that cotton effect? I think I have just lost some slides here. Okay, I will just check. If on approaching the region of cotton effect from the long wavelength, one first passes through a maximum and then a minimum, the cotton effect is said to be positive. Suppose when they are plotting a graph between wavelength and your optical rotation. So what you do, you first uh, decrease your wavelength. So if first you see a peak, then you get passes through a minimum, then the effect is said to be positive. Uh, and on the other hand, if the trough is observed first, by you just see when we are decreasing the wavelength, first a trough is in, means first your dispersion is less, then we are getting a crest. Okay, maximum, first we are getting a minimum and then we are getting a your maximum. So in that case, that is known as your negative cotton curve. So not negative cotton effect. So in positive cotton effect, with your decreasing in wavelength, first you are getting a peak and then you are getting a trough. But in case of negative cotton effect, first you are getting a trough and then you are getting a peak. This cotton effect curve is more important for deciding the stereochemistry or the configuration of a molecule. You just do the absorption spectra and study the cotton curve. Okay, so there are some axial halo-keto rule. So in this sector rule, the space around the chromophore is divided into quadrants or octants. Okay, and the contribution of any substituent to the cotton effect depends upon their position in the sector. The rule is applied when an axial hydrogen, okay, not your equatorial hydrogen, that does not contribute to cotton effect. So you cannot see the equatorial hydrogen in cotton effect, but if your axial hydrogen is there, then that contribute to your cotton effect. So in case of axial halo-keto rule, what it says that if the axial hydrogen is present at alpha position, appears to the right hand side of the observer, then the compound will show a strong positive cotton effect. Suppose this is your observer, you are seeing from this side, and the axial halo group is present just right to the observer, then that would show a positive cotton effect, or vice versa. You are just giving this compound, taking the actually ORD, then you are seeing a positive cotton effect. Then you can just say that this would be your confirm. This would be your confirmation configuration. So when you are looking from and when you are looking and the halogen group is present left to your the observer, in that case that gives you a strong negative effect. So these two are, if you just see, these two are actually mirror images. So when it is giving when your observer actually from the observer the axial group is present to the right hand side, and here from the observer the axial halogen group is present on the left hand side. And when it is present in the left hand side, it would give you a strong negative effect, and when it is present on the right hand side, it is going to give you a positive cotton effect. So there is an okay. Then this octant rule. Okay, yeah. So if you just see when this halogen group is present, you are looking from this side, if your halogen is present on the positive quadrant, if it is present on the positive quadrant, then that would give you a positive cotton effect curve. But when that is present in your negative quadrant, then that is going to give you a negative cotton effect curve. So suppose in this molecule, from this trans 2 decalon, when we do the bromination, we can either get this S isomer, S enantiomer, or the R enantiomer. Then we do the ORD spectra. So if we get a positive cotton effect, then we can just say, okay, this bromine has to be on the right side. So this would be as it is giving you a positive cotton effect, so we can just say the confirmation is this bromine is on the right side. If you get a negative cotton effect, then you can just say that bromine would be on the left side. But actually this is the it is giving you positive cotton effect, that means this bromine is on this side. So from actually ORD spectra you can determine what is your product and what is the configuration of your product using this alpha haloketo rule. That is in your cycloketones actually. Suppose this compound and this compound bromine actually this position, okay, in this position. So if bromine actually is on the left hand side, it can be, or it can be on the right hand side. Actually this gave your negative cotton effect. So the stereo or so the configuration of your stereoisomer is bromine in actually in this side left to your carbonyl group. Next comes your octant rule. According to this rule, the space around the carbonyl group is divided into 8 sectors called octants, like this: minus plus plus minus minus plus plus minus. And the rear sector, actually the rear sector contributes more to the cotton effect. Suppose this is your carbonyl group, so it is given 4 octant minus plus plus minus, and this is the rear one plus minus minus plus. And then the molecule is again viewed from the side of the carbonyl group. The contribution of the substituent present in different sectors will decide whether it was going to give you a positive cotton effect or a negative cotton effect. So the mostly we are doing it in case of your cyclic ketones. So this cyclohexanone, you view it from this side, so you just see, you number it like this: 1 2 3 4 5 6. So there are some rules. Contributions from hydrogens are normally not taken into account. The fourth carbon atom lies on the actually YZ nodal plane. So this group present at the axial or equatorial position at C4 do not contribute to your cotton effect. Next is, similarly, the substituents present at your C2, okay, this is C2 equatorial position and C6 equatorial position, are near your XY nodal plane. Hence, equatorial substituents present at C2 and C6 positions have very small contribution to the cotton effect. But as the axial substituents, So this has to be your axial, this one is your axial. At C2 and C6 lie away from XY plane, they contribute more towards the curtain effect. So C4 does not contribute. At equatorial positions at C2 and C6, they do not contribute, but the axial positions from C2 and C6 that contribute strongly in the curtain effect. There is equal contribution by substituents present at C3 and C5 carbons. The substituents present at C2 and C5 have positive contributions, whereas the substituents present at C3 uh, and C6, it should be C6, make negative contribution to the curtain effect. Okay, so suppose you just take the example of these three cyclohexanones. Either it is in your axial or in your equatorial position. So you just have to do it, not this is 3 cyclohexanone, but you have to give the numbering according to this figure. Okay, so 1 2 3 4 5 6, and in this case 1 2 3 4 5 and 6. So you see, in case of this enantiomer, the CH3 group is present at the positive octant. So 5 have positive contribution, so that means it should give you positive curtain effect. Okay, and when it is present in the rear sect 3, so this would give you negative curtain effect. So from this you can say like which one is which enantiomer. Okay, if this one R methyl cyclohexanone exhibits a positive curtain effect, and this S is giving you a negative curtain effect. Similarly, if you see the transdecalone, 10 methyl transdecalone, okay, it can have uh, two stereoisomers, either this one and this one, but it gives you a positive curtain effect. So you just number it according to your however it was 1 2 3 4 and 5. So you have a substituent at 5. So if as you are having a substituent at 5, then it should give you a positive curtain effect. But in this case 1 2 3 4 5 6, so you have a substituent at 3, so that gives you a negative contribution, so that gives you negative curtain effect. So from this you can just say which conformation you are having or which enantiomer you are having by using this octant rule, which says that whichever substituents are having in your positive quadrant or positive, that gives you positive curtain effect, and the C3 and C6 or those who are present in your negative quadrant, that would give you your negative curtain effect. Okay, next is your helicity rule. What is helicity rule? Yesterday I have talked about helicins, where the molecule is either coiled in a clockwise manner or in a anti-clockwise manner, or right hand or left hand. So this rule states that right-handed helix, or that is also known as your p helicity, leads to a positive circular dichroism, and while a left-handed helix or metahelicity, that is known as your M, which one is left-handed, that is termed as M helicity, that would lead to your negative curtain effect, or P will lead to positive curtain effect. So what is helicity? Helicity is the chirality of a molecule that has a helical or screw-shaped or a propeller-like structure. Helicis, okay, P helicity, that is spirals your downward clockwise along the helical axis. Like we know that our DNA is a helical molecule. Okay, it goes like this. So M helicity, that spirals downward anti-clockwise. So if you just see this carbon double bond, they are in the anti-clockwise, in the clockwise manner. So this is named as P, and in this case, this carbon is just on this side, so that is in your anti-clockwise manner, that is named M. Similarly, this one is P, this one is M, alpha beta unsaturated ketone, and this is your conjugated diene. So the ORD curves from this, actually, if we just see the ORD curves, we know that P gives your positive cotton effect, and P helicity gives positive cotton effect, and M helicity gives you negative cotton effect. So when we do the 2,4 dienes, you can just determine the structure and whether it is P helicity or M helicity from your ORD cotton effect curves or cotton curves. And so P helicity molecules gives you positive cotton effect, and M helicity your molecules give you your negative cotton effect. Okay, while doing this cotton effect, actually positive helicity, however, when they do it to n-pi star transition, actually, like when we have a carbonyl group, there is a chance of your pi star transition, and you have a n-pi star transition. So these transitions actually occur at different wavelengths. So what he studied that, okay, pi star in case of pi star transition, because you are seeing the effect at a certain wavelength region. So pi star comes around actually 360 nanometers something. So when he did the cotton effect curve during this around this 360 nanometer curve, he get a positive cotton effect for pi star P helicity, and negative cotton effect for your M helicity. But in case of your n pi star transition, which occurs at actually 300 to 350 nanometers, he got a difference. Like P helicity gives your negative cotton effect, and uh, positive cotton effect was given by your M helicity. So that also depends on which kind of transition you are observing. But mostly P helicity gives a positive cotton effect, and M helicity gives a negative cotton effect. So they are doing the transitions like depending on which kind of molecular transition they are observing. So in case of helicine also, they have the same rule here. The P helicins, this, if you just see, this one is anti-clockwise. Okay, so this one is M helicin, and this one goes in your clockwise direction. So that is your P hexahelicin, this is your M hexahelicin. So this gives you a positive cotton effect, and this gives you a positive cotton effect, and this gives you a negative cotton effect. Even this two alpha beta, no, this is not alpha beta, but still this is a beta and gamma. Unsaturated ketones, this exists in this type of conformations. Here also, if you just see, this one is a right-handed helix, this one is a left-handed helix. So this one is P, this one is M, and so this gives you a positive cotton effect, and this gives you a negative cotton effect. Next is Lewis rule, which we have already discussed yesterday for the determination of configuration in allenes, optical active allenes, where you have a chiral axis. Okay, where you have a chiral axis. So I have already told that in this case, the allenes are projected in such a way that the more polarizable substituent is placed at the top in the vertical position as shown below. Suppose you are viewing it from this side. So chlorine on top and hydrogen on down. And this one would be given priority number 1, and this one would be given priority number 2. As you are observing from this side, so these two will be given more priority as compared to these substituents. Now then one would be priority number 3, and this one will be priority number 4. And they are actually, when you are viewing from this side, your CH3 group is on right and hydrogen is on left. So this one is 1, 2, this one is 3. So this one is a S configuration. This is your Lewis rule, which we have already discussed yesterday. And suppose for this allene, you are viewing it from this side. So when you are viewing it from this side, now these are or you have to put this CH3 and H on your horizontal path. So your CH3 is on left and hydrogen is your right, and chlorine is again on your top and bromine right. So this one, this is priority number 1, this is priority number 2, this is priority number 3, this is priority number 4. And in this case you do not have to reverse your configuration whether H is on horizontal or vertical, because this is not a horizontal and vertical axis, we are just viewing it from different directions. So in this case, when we trace the path from 1 to 2 to 3, it gives you a R configuration. Suppose you just look it from this side, so in that case your, when you are looking it from this side, that is going to give you the same configuration. Okay, so in this case this is 1, this is your, okay, I just got it, this one would be hydrogen CH3 on your right hand side when you are viewing from this side. So CH3 on the right side, so 1 2 and this is your 3, so this is also giving you R. So whether you are seeing it from this side or from this side, it is going to give you the same configuration. So that's all for today. Thank you. If you have any doubt, you can ask me, we can discuss. Any doubt? Just check. I'm here for 5-10 minutes. These things you have to visualize a lot actually, and you have to do a lot of practice. And don't worry about like why these uh, things are there. You have to just suppose in this octant rule, you have to remember this figure and then what is the position and this rule, and accordingly you have to name this projection formulas. Then just see whether the locant is on which place, whether it is having positive contribution or negative contribution. So actually this spectra gives a detail that whether you are going to get this compound or this compound. So that is a bit easier actually. You do not have to do any kind of your quasi-racemate, any chemical selection. Just you are going to give it to your spectrophotometer that will give you a actually graph, and from that graph you can just distinguish whether you are having a positive cotton effect or a negative cotton effect. So in that case you can just uh, assign your molecule which configuration it is having. Okay, so this is a lot easier after spectroscopy. Actually it is a lot easier to determine what kind of compound we are having. If we are having this compound, then what is the stereochemistry of this one, whether it is R or S, you can easily determine from actually spectroscopy techniques. So maybe in your next semester, I don't know whether you are having spectroscopic techniques, but I think you must have studied UV, IR, NMR in your BSc classes. So that determines a lot about what kind of compound you are having. And in NMR also you can differentiate between your actually diastereotopic hydrogens. You can differentiate in NMR also. So if anyone is having any doubt, please go for it. You are free to ask. Okay, I will talk with your actually IGNO center. If they say so, I can just share my PPTs. Okay, and they will send to you maybe. But I will, yeah. And if you have
Okay,
any,
madam. Thank you, madam.
yeah, any other questions or queries, if you have, you can ask me.
मैम टॉपिसिटी
टॉपिसिटी
आज्ञा
अच्छा ओडिया रे कहबी
हाँ ओडिया रे कहले आहुरी भलो
ଭଲ ବାକି ସମସ୍ତେ ଓଡିଆ ଜାଣୁଛନ୍ତି ତ
हाँ मोस्ट ऑफ दी जानिबे
अच्छा ठीक ଅଛି ओके ओके
मैम ऑफलाइन क्लास हे परिबोनी
ऑफलाइन क्लास केमती हबो ମୁଁ ଜାଣିନି ସେଟା ତମେ ସେଣ୍ଟରରେ ପଚାରିବ ଆମକୁ ସେମାନେ କଣ୍ଟାକ୍ଟ କରିଛନ୍ତି ଅନଲାଇନ୍ କ୍ଲାସ୍ ପାଇଁ ଅଫଲାଇନ୍ କ୍ଲାସ୍ ପାଇଁ ସେମାନେ କହିବେ ମୁଁ ତ ଜାଣିନି ଆକ୍ଚୁଆଲି ହେଲା
ओहो
ହଁ ତ ଟପିସିଟି ହେଉଛି ଆକ୍ଚୁଆଲି suppose you have two hydrogens here okay you have two hydrogens in this carbon on this carbon okay so now if you just see these are only hydrogens ସେମାନେ କେବଳ hydrogen ସେମାନେ identical ବୋଲି ଲାଗିବ but ସେମାନେ ଯେତେବେଳେ ଗୋଟେ molecule ର part ହେଇ ଯାଉଛନ୍ତି okay so ଗୋଟେ molecule ର part so they may be distinguishable or may not be distinguishable suppose when we just treat it or we replace it by one fluorine okay ୟାକୁ ଯେତେବେଳେ ଆମେ replace କରୁଛେ we are getting this enantiomer ଯେତେବେଳେ ଆର ହାଇଡ୍ରୋଜେନ କୁ ରିପ୍ଲେସ କରୁଛେ we are getting a different enantiomer so that means these two hydrogens place are different in space actually ସେମାନଙ୍କର position ଗୁଡାକ different ଅଛି their position is different so this special relationship means space ରେ ତାଙ୍କର relationship ଟାକୁ ଆମେ କହୁଛେ topicity ଯଦି ସେମାନେ same compound ଦଉଛନ୍ତି then those are known as your homotopic କେତେବେଳେ ଦେବେ ଯେତେବେଳେ ଏଇ ଦିଟା ଗ୍ରୁପ ମଧ୍ୟ ସେମ୍ ଅଛି ତେଣୁ ୟାକୁ ତମେ ରିପ୍ଲେସ କର କି ଯାହା କର ୟାକୁ ରିପ୍ଲେସ କର କି ୟାକୁ ରିପ୍ଲେସ କର you are going to get the same compound so that is known as your homotopic କିନ୍ତୁ ଯେତେବେଳେ ଏଇ ଜାଗାରେ ତମେ ତାକୁ ରିପ୍ଲେସ କରୁଛ so you are getting if you are replacing this hydrogen you are getting a different enantiomer and if you are replacing this hydrogen you are getting the other enantiomers so a case re you are getting two different enantiomer by replacing these two hydrogens so now these are distinguishable you can distinguish this one and you can distinguish this one so this is known as your enantiotopic hydrogens okay and when by replacement you are getting diastereomers then those hydrogens are known as your diastereotopic hydrogens or diastereotopic atoms if you are replacing the groups or any other atoms then diastereotopic atoms ବୁଝି ପାରିଲ ତ
आज्ञा आज्ञा
ହଁ
बुझिला
ଆଉ କିଛି
एमटी ऑक्टेन रूल टा आउथरे टिके खाली
octant rule ओके ऑक्टेंट रूल टा कहूची तमरो एक्चुअली जे कोनसी carbonyl group the space around the carbonyl group is divided into 8 sub sectors तमे carbonyl group जदी एमिति देखिबो एट जो अछि okay yeah if you see it then it is divided into 8 sectors front sectors and rear sectors so these are the front sector minus plus plus minus but if you just see the substituents are present in your rear sector substituents are present in your rear sector ତେଣୁ rear sector ରେ ଯୋଉ substituent ଗୁଡାକ ଅଛନ୍ତି ତାଙ୍କ position ଉପରେ ହିଁ ତମର cotton effect ଟା show କରିବ ସେମାନେ ଯଦି positive quadrant ରେ ରହିବେ ତାହେଲେ positive cotton effect ଯଦି negative quadrant ରେ ରହିବେ negative cotton effect show କରିବ that's all ତମର octant rule rear sector ଟା determine କରୁଛି ଆଉ ଯଦି ତମର substituent ଟା positive ରେ ରହୁଛି କି negative ରେ ରହୁଛି ତା ଉପରେ cotton effect show କରୁଛି ତେଣୁ again ତମର क्लिक किटोन जदि अछि त हम ताको नंबरिंग एमिति ही करिवो ये जेमिति अछि ए फिगर टाको मन रखिवो सो दैट हैज टू बी इन दिस वे अगेन जो गुडा को जो सब्स्टिट्यूट गुडा को पोजीशन नंबर 4 रे अछंती तांकर कॉटन इफेक्ट सहित कोनोसी इफेक्ट नाही कॉटन इफेक्ट रे तार कोनोसी कंट्रीब्यूशन नाही इवन व्हेन द पोजीशंस एट इक्वेटोरियल पोजीशन एट 2 and 6 हेले तांकर मध्य कोनोसी कंट्रीब्यूशन नाही टुवर्ड्स कॉटन इफेक्ट 3 and 5 रे जो जो गुडाक अछंती आइदर एक्सियल हो और इक्वेटोरियल हो equatorial or axial, they have contribution towards cotton effect even when you have a position or you have a substituent ଯେତେବେଳେ position number 2 ର axial ରେ ଯଦି ଗୋଟେ substituent ଅଛି or 6 ର axial ରେ ଯଦି ଗୋଟେ substituent ଅଛି they have contribution towards your cotton effect. So କେମିତି ରହିବ ଯଦି ତମର ସେ କହୁଛି substituents present at carbon number 2 ଆଉ carbon number 5 ସେ carbon number 5 ର axial ହଉ କି equatorial ହଉ सेमानकर पॉजिटिव कंट्रीब्यूशन अच्छी that would give you a positive cotton effect आउ कार्बन नंबर 3 and 6 रो they would give you a जदि substituent सही जगह रे अच्छी that would give you make negative contribution. So you just see in methyl cyclohexanone, okay, this methyl cyclohexanone can have two enantiomers. If you just see they are the same तांकर केवल configuration different अच्छी, okay, they have different configuration but they are just the mirror image of each other. तेणु तुमको दिया गला गोटे methyl cyclohexanone. You do not know which enantiomer you are having. Suppose you get the positive cotton effect. That means your CH3 group is present in the positive quadrant. So if you just draw these two molecules, so तमे से देखिबो कि तमरो ए molecule रे तमरो CH3 group टा positive quadrant रे रहउची. तमे एठी सेही हिसाब रे से जो पूर्व फिगर हिसाब रे पोजीशन देखिबो 1 2 3 4 5 6 तो एठी देखिलो तमरो सब्स्टिट्यूएंट ता CH3 टा कोठी अछि 5 रे अछि सो दैट इज इन द पॉजिटिव क्वाड्रेंट सो दैट वुड गिव यू ए पॉजिटिव कॉटन इफेक्ट एंड तमे सेथु जान दबो कि दैट विल ए जो कंपाउंड ता हमरो दैट इज योर दिस कंपाउंड ओके जदी आरटा हे थांदा इन दैट केस द सब्स्टिट्यूएंट इज प्रेजेंट इन द थर्ड पोजीशन ओके जदि थर्ड रे रहउची थर्ड रे रहिले दैट वुड गिव यू ए नेगेटिव कॉटन इफेक्ट तेणु तुमको जेतु नेगेटिव न दे कि पॉजिटिव दोची सेतु तुम जानि परिबो कि ओके द कंपाउंड इज हैविंग दिस आइसोमर हैला हमर कंपाउंड ता ए एनांसियोमर नो सिमिलरली ए जो ट्रांस कोच हां ट्रांस डेकानोन 10 रे गोटे तमरो 10 methyl trans decanone in this case तमरो सेठी देखिबो कि that is also giving you positive cotton effect तेणु सेथरु जानि परिबो कि को कंपाउंड ता तेणु याकु मध्य नंबरिंग सेमिति ही करिवो 1 2 3 4 5 6 तेणु यार 5 रे होची तमरो सब्स्टिट्यूएंट अछि बट इन दिस केस you have the substituent at position number 3 so this would give you a negative cotton effect and this one would give you a positive cotton effect जदि पॉजिटिव दोची ताले तमे जानिबो कि एटा होची एनांसियोमर ए एनांसियोमर ता प्रेजेंट अछि जदि नेगेटिव देला देन यू नो दैट दिस एनांसियोमर इज देयर बुझि परलो
आगे मैडम आगे
आउ किछि डाउट okay I think we can just end our class here today if no one else is having any doubt. Stereochemistry, we finished stereochemistry today. From tomorrow we will have reactive intermediates. In reactive intermediates we have carbocations, carbanions, carbines, nitrines and arenes. Okay, so their stability, structure and their reactions, some rearrangements, we will study those things. Okay, so that's all for today. Thank you.
थैंक यू मैम
Thank you, ma'am.